Hi, in this video, I'm going to give a very brief overview of the particles that are described in the standard model, and just basically discuss the way they are categorized. And then I'll discuss these particular categories in different videos in more detail. So this is really just a brief overview. So again, what is the standard model? This is the way that physicists understand the way all of the fundamental particles that we know of interact with each other. And it's based in the framework of quantum field theory. So if you look up standard model and you do a Google image search, you'll probably find a chart that looks something like this. So this is a sort of summary of the particles in the standard model and the way we categorize them. We'll see this is actually not all of the particles, but more on that later. So how are things organized here? On the left side, so these particles that appear in purple, which are our quarks, and the particles which appear in green, which are our leptons, these together are our fermions. And these are sort of your matter particles. So the electron, which is probably the most familiar particle from the standard model, it's a fermion, so it fits in this category. The right-hand side are our bosons. So this includes our force-carrying particles. So for instance, the photon, this is a particle of light. It's the particle that carries the electromagnetic force. So all of these particles in orange carry the forces, and then the Higgs boson is sort of in its own category, and we'll learn more about that later in the course. So those are our bosons. One particle missing from here is a particle known as the graviton, which is said to be beyond the standard model because the graviton, which would be a particle carrying the force of gravity, is not currently explained by the standard model as we know it. Okay, so back to our fermions. The fermions are split up into two colors. We have our purple ones on top, which are our quarks. And one way we can think of the quarks is the quarks are the particles in the standard model that interact with the strong force, which is to say gluons. They can exchange gluons between each other. Gluons are the particles which carry the strong force. So these interact with a strong force. Below them, we have the leptons, and we could say these are the fermions that do not interact with the strong force. So really, whether they interact with the strong force or not is a good way of distinguishing between these two types of particles. And again, we'll dive more deeply into the specifics of quarks and leptons in a future video. So let's zoom in on one of these boxes. You'll have noticed there are numbers that appear in these boxes. What do these numbers mean? Let's look at the electron, since again, this is probably the most particle which is familiar to you. So if we look at this box, the number which appears on the top is the mass of the particle. So an electron is it's said to be about half an MeV, which EV here is electron volts. Below that, we have the electric charge, and then the bottom number is the spin. And it's important to note the number here, you'll notice there are no units on our electric charge or our spin. That's because these are listed as a multiple of, for charge, it's of the charge of the proton. And for spin, it's a multiple of Planck's constant h bar, and the values are given here below. So you'll notice E, which we all list as, often we say, the fundamental charge, although quarks have a fraction of this charge. So whether it's fundamental or not is maybe up for debate. The E is the proton charge, even though E is like electron. And I say that because E is always taken to be a positive number. And so you'll notice in this box, the electric charge is listed as -1. So it's negative E, where E here is a positive number. So don't get your signs mixed up there. Let's look at one more particle, which is maybe the second most familiar one. Probably depends on your personal background, but the photon, right? This is the particle which carries the electromagnetic force. It is a photon, which is sort of a particle of light. So photons are massless. You'll notice this first number is 0. It does not self-interact which is to say it doesn't have any charge. The photon itself is not charged, it does not have an electric charge. And then it has spin 1. So it's a boson, which means it has integer spin, which we'll discuss in the next video. All right, so what's another way we can categorize our particles? If we go back to this chart from before, you'll notice this sort of Roman numerals 1, 2, and 3 at the top. That's listing generations. And so this first column here is said to be the particles in the first generation. So we have first generation quarks and first generation leptons. And then we have our second generation and our third generation. One of the things that you will notice about these generations, and one of the important things about them, maybe most important, is that you have mass increasing to the right. So again, if we go back through those, our first generation are our lightest. So the up is lighter than the charm, which is lighter than the top. So it's not necessarily, you don't want to be comparing your quarks to leptons or anything when we're talking about relative masses. But within each row, you'll notice mass is increasing to the right. So if we go down to our leptons and look, the electron is lighter than the muon, which is lighter than the tau. And we'll see when we talk about leptons, for instance, this is important because heavier particles are always going to want to decay into smaller to lighter particles. And so a tau is always going to want to decay into either a muon or all the way down to an electron. A muon is going to want to decay into an electron. And then since an electron, there's nothing lighter, an electron is a very stable particle. And we learned that's why there's an abundance of electrons in nature, because of that fact that they're stable, they're first generation. That means there's not going to be a lighter particle for them to decay to. So this is not all of the particles in the standard model. So one thing that we'll discuss when we learn more about quarks is that quarks have color. And so these 6 quarks that are listed here are not actually all of the quarks. In some sense, you could say there are many more, because the quarks can come in different colors. So we'll learn, for instance, there's a red quark, there's a green quark. So like the up comes in different colors, which are different particles actually. But since color isn't listed on this chart, that's sort of more, so it would be a lot of redundant information. So this is a really compact version of all of the elementary particles. Furthermore, we also have all of the antimatter. So antimatter appears a lot in sci-fi, but antimatter is actually a real thing, even though the way it appears in sci-fi is often not correct. There is indeed antimatter in the universe that we have lots of experimental evidence for. And you'll notice this chart nearly doubled in size. And what you'll see is for every quark that we had before, so we had 6 quarks, there are now 6 additional particles, which are anti-quarks. So for up, we have an anti-up. For down, we have an anti-down, etc. And physicists are pretty practical in our naming conventions, actually. So the anti-particles, generally you just write the word anti in front. And then it's really easy to know what you're talking about. The anti-up is the anti-particle partner to the up. The only one that's a little different is you'll notice that the anti-electron has its own name, it has a positron. And that's, of course, just for historical reasons, the positive electron, so a positron. But all the other particles, you just add that word anti in front. And what's the difference between a particle and its anti-particle partner? Well, if you look, let's look at the up and then the anti-up. So, take a minute to look at those 2 boxes, find the anti-up and the up, and see what's different about the numbers. Well, right away, you'll notice the masses are the same, 2.2 MeV. The spins are the same, they're both 1/2. And the only thing that's different is that the charge is an opposite value. So this is the primary difference when we look at particles and their anti-particle partners. is that they have the same mass, the same spin, the same magnitude of charge, but it's going to be the opposite sign. So if we look at the down and the anti-down, the down is a negative 1/3 charge, and the anti-down is positive 1/3. The electron has -1 charge, the positron has +1 charge. And so this is how we distinguish between particles and antiparticles. You might wonder, neutrinos, we haven't talked about neutrinos yet, but neutrinos are on our bottom row. Neutrinos are neutral. Well, that's why they're called neutrinos, right? In part, they're neutral. And so if their mass is the same, their charge is the same because they're neutral, and their spin is the same, how are anti-neutrinos any different from regular neutrinos? And this was a valid question. Scientists at first didn't know if the neutrino had an antiparticle or if it's said to be its own antiparticle. We now understand there is actually a difference, which is way beyond the scope of this video. But there are indeed anti-neutrinos, and we do know that they're different, and we will talk about that in future videos. The photon, on the other hand, it's another neutral particle. It's said to be its own antiparticle because it does not have an antiparticle partner. All right, so that's our overview of the standard model, and we'll dive a lot more deeply into these topics in future videos. Thanks for listening.